Okay, race fans, we're back for round 2 with gas laws with Mr. T. This gas law we're going to talk about is Charle's law. Last one was Boyle's law. The variables and constants are going to be slightly different. Remember, we have 4 variables when directing with gas laws: pressure, volume, temperature, and number of particles. When working with Charle's law, the variables are going to be volume and temperature. What's being held constant in Charle's law is pressure and the number of particles. So each one of these we're talking about initially will have 2 variables changing, 2 things being held constant. In Charle's law, you got volume and temperature. So we're going to talk about how are those impacted. So an example of that might be you got a balloon and you got a birthday party. It's middle of January, or this year it's April. It's cold outside. You get the balloon at the store. It's all blown up. You walk outside. You put it in your car, and it's January in Iowa, and it's like 5 degrees outside. So temperature drops significantly. So that nice inflated balloon in the store went outside where it was nice and warm. Now it's really cold. What's going to happen to the size of that balloon? The space takes up. Well, yeah, most of you are thinking it's going to get smaller. Why? Well, that temperature, as it gets colder, the particles slow down. If they're not moving as fast, that means they're not hitting the sides as much. There's less collisions. Okay? The pressure will stay the same, but since the pressure, the volume is going to become less to keep that pressure the same. Inside the balloon, the number of particles is going to change. So as the temperature gets colder, the pressure, staying the same, the volume will get less. Okay? So that's the same thing. If you get a balloon in the summer, it's August in Iowa, when you take it, put it in your car. Okay? Temperature goes up. The volume is going to expand and get really big before it pops, okay, to keep the pressure the same. So that's about the best example I can give you. Let's talk about that relationship. So you have temperature increases, the volume's going to go up. Well, if the temperature goes colder, it's going to go down as well. So you have what we call a direct relationship. That relationship is going to be what we call a direct. A direct relationship is when both variables are headed in the same direction. Temperature goes up, volume goes up. Temperature goes down, volume goes down. Okay? It's kind of like a relationship if you have a job. The more hours you work, the more money you make. That's a direct relationship. The less hours you work, the less money you make. Direct relationships, if you were going to chart them on a graph, will always be on an incline, increasing chart. Because as one goes up, the other one's also going to go up, or as it goes down, it will also go down. Now, as you saw in Boyle's law, an indirect relationship was multiplication, P times V. Now we have a direct relationship. So a direct relationship isn't going to be multiplication, it will be division. Okay? So the formula for that will be your initial volume divided by your initial temperature equals your secondary volume divided by your secondary temperature. That's the basic formula. Again, pressure and number of particles are being held constant. Okay? Let's kind of do another example setup working with our temperature and volume. So, if I had a syringe, okay, just an everyday syringe, and the volume, I don't know if you can see that with the camera, if it was set at 20 milliliters, and an average classroom is about 20 degrees Celsius. So don't make fun of my drawing, but say here's our syringe, okay? So here's our syringe, there's the bottom of the tube, okay? And then here's the syringe part with the plunger going up. And let's say we have 20 milliliters in there. And the temperature in the room is 20 degrees Celsius. So let's say we cut the volume in half. Okay. Or I'm sorry, let's say we cut the temperature in half. So the temperature drops to 10 degrees Celsius. It's colder. What should happen to the volume? Well, if it gets colder in here, that volume should shrink. So the volume should come down to about 10 milliliter, right? Direct relationship, they should drop about the same. Well, what happens if I drop it to 5 degrees Celsius? Cut it in half again. The syringe volume should drop probably about 5, right? 5 milliliters? Well, what happens if we drop the temperature to 0? Some of you are right now thinking, well, they go to 0 also. Some of you are saying, wait a second. Can we have 0 volume. Remember, the number of particles isn't changing. There's got to be gas in there, right? So can we have no volume? What about this question? What if we go all the way to negative 10 degrees? Negative 20. Can you have a negative volume here? No, you can't. So how do we solve that problem? There's got to be something in that syringe. Well, the problem is our temperature. We can't have negative volume, but the relationship has to be the same. So we have to use a temperature system called kelvins. Kelvins does not have negative numbers. Absolute zero is 0 degrees Kelvin. How do we calculate this? So anytime we have temperature in Celsius, we have to convert it to kelvins. And it's really simple. We take whatever our degrees Kelvin equals whatever degrees Celsius we have, and we add 273. So for example, if you had a temperature at 20 degrees Celsius, you add 273 to it, the degrees Kelvin are 293 degrees Kelvin. The reason why is we can't work with negative numbers. We can't have negative volumes. Okay, let's try a practice one here. We'll do one sample problem with Charles' law like we did with boils. First thing, let's make our list. Okay. It says we have a sample gas that occupies 6.8 liters. There's V1. 6.8 liters. At a sample temperature, 327 degrees Celsius. What will be its volume in milliliters? That's V2. X milliliters at 27 degrees Celsius, temperature 2. Just like in all of them, make our list. Okay. Now let's look at our units. Do we have it all the same? We have milliliters and liters. Let's do conversion. So we get 6,800 milliliters. Okay? Units there, good volume. Temperature, Celsius. Remember, we can't use Celsius, Fahrenheit. We got to convert it to kelvins. So we're going to add 273, which means our kelvins works out being 600 degrees Kelvin. Add 273, 300 degrees Kelvin. Now that our units are good, now we can plug them into our formula. Direct relationship, V1 over T1 equals V2 over T2. I plug my numbers in. Volume 1 was 6,800 milliliters. T1 was 600 degrees Kelvin. V2, X milliliters, we're trying to find a volume. T2, 300 degrees Kelvin. Now we turn into algebra problem. So we're going to solve for X. I'm going to cross multiply, get everything on the same plane. So I got X milliliters times 600 degrees Kelvin equals 6,800 milliliters times 300 degrees Kelvin. Now we're back to Boyle's law. Get X by itself. That cancels out. 600 Kelvin. That cancels. 6,800 milliliters times 300 divided by 600 should give us 3,400 milliliters. Does that make sense? Okay, check your answer. Your temperature got cut in half, got colder. So if the temperature got cut in half, the volume should be cut in half with what we got. Thanks for watching the Tippett Network.